Hello, everyone. Come on in. Come on in. It's like I almost got as many as I got for lab this morning. Anybody have any questions before we get started? All right.
Well, actually, yeah, I have a quick one. When's the next test or quiz?
I'm planning on putting out the practice test today, and then probably what I'll do is I'll give you the test like Friday, but I'll give you till Wednesday or Thursday to get it done.
Okay, thank you.
Because I usually like you to have 7 days with the practice test.
It'd be great. I got big plans.
What would it be on? Chapter 36 and
yeah, the last one we did was through chapter 8. So this will be actually this one might be 9 and 10 if the last one was 8. So it should just be 9 and 10. And then the next one will have 36 and 11.
We're still on 36, right?
Yes. Yep.
Cool.
Yep. Still on 36. And as a day, I wasn't expecting that we lost last time. So we'll have to work with that. All right. Anybody have any other questions? All right. So the last time we talked, I told you what the special theory of relativity was. Basically, there's two principles. The laws of physics are the same for all inertial observers, but I taught you how that really was just Einstein's way of cutting out gravity. Really pretty neat in that he just took the bull by the horn and suggested, okay, gravity's not a force. Forget it. Okay. Which is pretty bold. Of course, Newton had issues with it, and everybody else since Newton had issues with it, but still no one just said it's not going to be a force. But that's pretty much what Einstein did. And then his second principle was that the speed of light is a constant independent of the motion of the source and the observer. And from that, I was able to derive a time dilation equation. And that basically told us that evidently when we measure a time interval, if I got 1 second, you're not necessarily going to get 1 second as well. You could get 2 seconds, or you could get a half a second or something like that. So that's, pretty odd. But that was time dilation, and we hadn't really worked with it yet. So I wanted to work a problem showing you how that's used. And then I want to bring up some other things that are ramifications of Einstein's theory of special relativity. So let's get started with talking about a muon. So it turns out there exist these particles that are created about 1,500 meters above the Earth's surface. And at 1,500 meters above the Earth's surface, they're basically created because there's an interaction with solar radiation and the solar wind with the upper atmosphere. And that actually makes these particles called muons. And muons are sort of like heavy electrons. They're like 1,000 times heavier than electrons, but they are leptons, just like electron is as well. So they actually behave somewhat like electrons. But here's the weird thing. Okay, they have an average lifespan of about 2.2 microseconds. And even if you let something travel for 2.2 microseconds at the speed of light, that's not enough time to reach that, to make that 1.5 kilometer trip. So we've got actually two problems here. One, we've got to be able to explain how does that muon make it to the surface of the Earth from our perspective. And then the other problem we have is how does the muon make it from the muon's perspective, right? So in the muon's frame, why does it make it? Because in the muon's frame, it's not moving, okay? So what I'm going to do is I'm going to assume that the actual gamma value is quite large, and I'm going to assume that it's traveling at a speed of 98% of the speed of light. Now, I mentioned to you guys before about the usefulness of making a little data table where you can put in various values of gamma, various values of beta, and get out other values. But specifically, I initially just talked about try to find all the values of beta for gamma being a whole number. So we looked at the whole numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And then I said maybe 10,000, 100,000, a million, 10 million, stuff like that. So let me share my screen real quick. I think I've still got it open. Hopefully I do. And I'm going to try to show you the spreadsheet that I did make, or I'm just going to look like a goober because for some reason it's not sharing. There it is. Okay. That is an entirely different Excel. Okay, well, I'll open it anyways. So this is from my 241 lab, which isn't that helpful, but I'm going to now open this and say file, open. Are y'all looking at an Excel spreadsheet right now? It doesn't have the little green box around it.
Oh,
Oh yeah, there it is. It's just taking a while. Whew. So I hit file. Let's see how long this can take. Oh, there it is, relativity gamma table. What I did was I put gamma down here being 2, 3, 4, 5, 6, 7, 8, 9, 10, 100, 1,000, and then jumped up to 1,000,000.
I'm still looking at the
And it
lab.
calculated. You're still looking at the lab?
Mm-hmm.
Let's do this again. Okay, screen share. It says my resources are really low, so I think it's Zoom from the previous class is still processing that data and it's taking forever. Let's try again. There it is. There that is. Yes. So y'all see this? So it turns out if you take gamma, which is 1 over the square root of 1 minus parentheses beta, you can get a nice result. And that's what I did here. It turns out that beta is equal to square root of gamma squared minus 1 divided by just plain gamma. And you can see that here by just say, look at that. So I took A2, which is my gamma value, I squared it, and then I subtracted 1 from that answer. And then I took the square root of all that. So that's gamma squared minus 1 to the 1/2 power. And then I divided it again by gamma. And that gives me an actual beta that's used. So I could put in anywhere on this table. I made blue boxes for anything that I could enter a value in. But I had already done basically 2 through 1,000,000 here. And you see that even to the number of decimal places I got here, 1,000,000, you really got to go to speed of light before you can reach it, at least the speed of light to like 12 decimal places or whatever. But this first one, gamma equals 2, is just 86.6025% the speed of light. That's actually root 3 over 2 in case you hadn't recognized it. So that's a kind of nice one. But what I'm going to do is I'm going to go right in between this number and this number. So right in between 5 and 6. And I'm going to call it just a flat 9.80, which is really, really close to 5. You're going to get like 5.001 or something got awfully small like that beyond 5. So this is a good thing to do. I recommend you be able to do the algebra to solve for beta in terms of gamma. And I recommend you be able to write this out. And then you can have things like proper time and proper length automatically calculated for you. I'm in the process of making one that automatically calculates the momentum and kinetic energy and all that good stuff. But that's a good thing to do. I'm going to stop sharing and go back to my document cam. So just what I did was I said gamma is defined to be 1 over the square root of 1 minus v over c squared. That's the definition of gamma. But we also use the abbreviation that beta is equal to v over c. Okay, so I can just replace that with a beta squared. So I'll see this is 1 over the square root of 1 minus beta squared, like that. Now, if I square both sides, I get gamma squared is equal to 1 over 1 minus beta squared. Well, that gives me 1 minus beta squared is equal to 1 over gamma squared. Now I can pull this beta over here and this over there, and I'll get 1 minus 1 over gamma squared is equal to beta squared. I can get a common denominator, and that's going to give me gamma squared minus 1 over gamma squared. That's equal to beta squared. Now, finally, I can take the square root, and I'll get beta is equal to the square root gamma squared minus 1 over just plain gamma. So that was what I did to make that table. Just the type of arithmetic that they expect a lot of you doing in special and special relativity, at least. Mostly it's algebra, not a lot of calculus in special relativity until you get to the really fringy parts of the problems. So there's a way of doing that. We had found, for instance, that delta t, the time an observer would see or would think you're measuring, while they're actually measuring on the side of the bank. So basically, if you said something lasted 2 minutes and you were riding on a train car passing me by, this is what I would call your 2 minutes. Okay, and it wouldn't be 2 minutes. Well, that time is equal to gamma times the proper time. And the proper time is the time measured by the person using a clock that's not moving with respect to them. Okay, so this person is measuring your time according to your clock, but your clock is on a train with you flying by, so they're not measuring proper time. And that was our time dilation equation. So what I have is a muon. So this is example 1, say. A muon has a lifetime of 2.20 microseconds. Of 2.20 microseconds. And is created at 1,500 meters above sea level. It is later detected at sea level and traveling at V equals 0.98 C. A, ignoring relativity how far can that muon travel okay, and B, how far can it travel when we account for time dilation. Okay, so A, you're just basically saying, okay, from our kinematics, we know that V bar is equal to X minus X0 over T, right? But this is actually a constant speed. So V bar is the speed and our X0 is 0. So we're just going to say X is equal to V times T. And of course, the V is 0.98. And then times C, which is 299,792,458 meters per second exactly. And then, of course, the time that it could travel is its whole lifetime. So that's 2.20 times 10 to the negative 6 seconds. And when we do that math, we have to find Mr. Younger's phone because his calculator battery died today. Okay, so y'all verify this calculation for me, everybody. 0.98 2997992 Now you don't have to use that many digits. I was just showing off. It's actually neat because it's exactly that number. It's that number to an infinite number of decimal places. And then I'll do 2.2 e to the negative 6. Multiply. I get 646.3 or 0.4 meters. Thank you. Okay, so clearly that's not enough. Not enough time to make it to the Earth's surface. But here's the deal. What we know is that moving clocks move slowly. So that muon's moving with respect to us, so its time is going to slow down. So what we can see is that in fact its time, the time that it experiences is delta t 0, and that of course is equal to the time that we observe, which would be 2.20 times 10 to the negative 6 seconds divided by gamma. Actually, I think I want to say that backwards. I mean, this is actually written right, but I wrote the equation right, but I want you to remember this. So the actual muon is going to measure a time delta t 0, okay, on its clock, and that's the proper time. And the proper time is the time when its clock is moving with it. Well, its quote unquote biological or mechanical clock is what decides that it's going to disintegrate and come to nothing. So that's the clock that's traveling with it. So the delta t that we see will actually be longer than the 2.2 microseconds, and it's given by gamma times delta t 0. And of course, gamma is going to be, well, I'll put the delta t 0, that's 2.20 times 10 to the negative 6 seconds. I'm going to divide that by the square root of 1 minus 0.98. This is the beauty of using a beta, by the way. You got times c over c, and then you're going to square it. So really, you're just putting beta in there. It's kind of nice. And then, of course, you got to take the square root of that whole thing. Now, when I do that, I'm going to do, let's see, 2.2 e to the negative 6. And then I'm going to take 1, and I'm going to subtract from it the v over c squared. So that's 0.98 squared. I subtracted 1 from, or 0.98 squared, which was like, you know, big number. And 1, when I subtracted that from it, was 0.0396. Now I'm going to take the square root of that. And then I'm going to divide 2.2 times 10 to the negative 6 by that. The square root, by the way, came out to 0.1989, 997, something, so on and so forth. So now I get 1.10 times 10 to the negative 5th. So by traveling at 99% of the 98% of the speed of light, I almost, well, I did. I increased its speed by a little bit over a factor of 5, because a factor of 10 would have been 2.2 times 10 to the negative 6, or excuse me, times 10 to the negative 5. But this is about half that, but a little bit larger than half that. So it's clearly a little bit over 5, which is exactly what we expected from our spreadsheet. So what we see is, from our standpoint, the reason why the muon made it was its clock, its biological clock, was running slowly because it was traveling with respect to us. So what we would have thought would have been too long of a lifetime, 1.106 times 10 to the negative 6 seconds, is actually what we experience as its lifetime when it's traveling at 98% of the speed of light. So that is, in fact, why we, the viewers that see the muon moving, why we believe the muon makes it to the surface of the Earth. The other side of the coin, though, is what if, remember Dr. Seuss, Horton Hears a Who, what if a who was living on the back of this muon? It has to agree that it made it to the surface of the Earth. If we didn't, it would be a paradox, which isn't allowed in science. So how does a muon make sense of that? To the muon, remember, the muon, to the who, the muon is not moving at all. The who is sitting on top of it, so it actually measures proper time along with it. But how could it possibly make it? Can anybody think? Anybody think of a thing that might cause it?
Distance dilation?
Yeah, it's a distance dilation, because remember, velocity only has 2 parameters. If we're going to call the speed of light a constant, then that means this over this has always got to be a constant. Well, we just saw that you can tweak that, so it stands to reason you must be able to tweak that too, because there's no way you can tweak this without making this change, unless you can tweak that, twist that a little bit. I don't know what word I was thinking of there. Tweak. That was the word, tweak. T-W-E-A-K. So yes, it turns out you can tweak distances as well, and that's called length contraction. So let's look at an example of length contraction. So length contraction. So let's say there's a spacecraft traveling with a velocity v, okay, from one place, let's say Earth, to another place, say Alpha Centauri. And that distance for it is called just plain L. It's not L0 because L0 is a distance called a proper distance that would be measured by someone that thinks the length is not moving. So this guy flying by the spacecraft sees one end of the length right here as it passes it, and then it sees the other end of the length pass it again. So this L is clearly moving with it. What we want to know is how long does this thing, this guy think it is? Well, this guy right here is going to say that L is its velocity times delta t0. But notice delta t0 is his clock time, right? So in other words, if we wish to know what it's going to be in reality, in other words, what's its proper length, then we have to figure out v times the regular time. So we look at our equation for time dilation and we see that delta t0, the proper time, is the time divided by gamma. So now I can say that's v over gamma times delta t. And now if you're looking at that, that turns out to be the time, the distance traveled for us is this, v times delta t. So when we're looking at it, we say, okay, this guy's moving at a velocity v, and it takes him this amount of time, but we're not moving with respect to it. So this is the right time to use for us. So this turns out to be L0 over gamma. And lo and behold, that's the formula for length contraction. L is equal to L0 over gamma is length contraction formula.
So L is the spacecraft's measurement of length, and then L0 is the Earth and Alpha Centauri's measurement of length.
Yes.
What is gamma?
Yeah, and make sure you understand what that means. The reason it's the spacecraft's measurement of length is because the spacecraft is moving across that length. That's why it's not, the spacecraft doesn't have proper length. Now, if you ask the spacecraft how long the spacecraft is, then the spacecraft would report the L0. But him moving with us would have to report the L in that case. Does that make sense?
So that's saying from Earth and Alpha Centauri, they're both stationary with respect to each other.
Right.
Okay.
Yep. And of course, that means their length between them, distance between them, is stationary as well. Okay.
What is gamma?
That's that same factor we had before, the 1 over 1 minus beta squared. That's going to come up over and over again. So it's that's why I stressed it's good to have like that little table and to play around with it, because you use it and everything. You're going to see a lot more today, in fact. All right, so now we're in a position to explain from the who's standpoint why the muon made it. So this will be example 2. According to a who living on the muon, I can't stop writing the M as a mu when I go to write the word muon. According to a who living on the muon, how did the muon make it to sea level, which is a 1,500 meter trip? Okay. So according to the who and the muon, they see the Earth and its atmosphere like this, and the Earth and its atmosphere are moving at a velocity v equals 0.98 c. So the atmosphere, so this is a solution. Whoa. So solution, the atmosphere is length contracted. To L, which equals L0 over gamma. So us that aren't moving with the atmosphere say that the length, which is not moving with respect to us, is just the 1500 meters. So I'll put 1500 meters, and then I'm going to have to divide by the gamma factor, which is basically 1 over the square root of something. We already know that value is roughly about 5, right? But I'll go ahead and put it in here. Since it's 1 over gamma, that just basically becomes 1500 meters times the square root of 1 minus 0.98 c over c squared. So we're going to get, like I said, it should be a little bit over 300 meters. Again, I keep grabbing a calculator whose battery's dead. That's not helpful at all. So I'm going to do drop 1500. And now I'm going to do 1. And I'm going to do 0.98 squared. And 0.98 squared, of course, is 0.9604. I'm going to subtract that from 1, and then I'm going to take the square root of the result, and I get 0.1999 or 0.198997, so on and so forth. So now I'm going to just multiply that by 5, or by the 1500, and I get 298.5. Actually, I'll say 0.496 meters. So what we found pre-relativity was that the thing can only make it 646.4 meters without relativity. Well, good news is the distance according to relativity is only 298. So it's more than enough time for it to make it to the surface of the Earth, thanks to length contraction. Any questions on that?
What is c? Are we using the speed of light for c?
Yes. Yeah, just most of the time, like if you can tell it as a percent, then the c's just cancel out.
I thought so. I just wanted to make sure.
Yeah, no problem. Oh, and I said it would be a little bit over 300. I forgot I was dividing by a little bit bigger than 5. So that means it should have been a little less than 300. And that's why it came out to that. Does that make sense how you use that? Go ahead, David.
So does that mean if like you're going to travel to like a distant star or something, if you're traveling at a speed close to the speed of light, it would take less time than it would take if you were using like Newtonian physics?
Yeah, but it's kind of a bummer because like if you don't take your whole family with you, then you're sort of screwed over because basically everybody's time clock continues to move really rapidly while yours slows down a lot. And that's what happened like in Interstellar when the dad came back and his daughter was an old lady. Basically he had been through a lot of different time dilations and had a lot of different problems. So he was, left when he was like in his upper 30s and came back when he was like in his 40s, and she was like in her teens when he left, and he came back and she was like 80 something. Which brings me to the next problem. This is called the twin paradox. So here we go with the twin paradox. So the two paradoxes I'm going to talk about, and there's another one called it's called Ehrenfest paradox. That's another one that's really interesting. But we're going to do the twin paradox right now. And I'm going to put the word paradox in quotation marks because in reality, it can't be a paradox or else physics is jacked up, and physics isn't jacked up. In fact, Einstein fixed it. So here's the twin paradox. And a lot of people get this wrong, including Time Life books. I know you've probably seen all the stuff that quote unquote Time Life book gives you. If you get a subscription to Time or something like that, they'll give you the phone, or they'll give you some kind of book or something like that. Well, I had one of these books on neat things about science by Time Life books. And lo and behold, I read it and found a big error in it, and that really bothered me. But let's imagine for a second that we have me, Billy, and I have a brother, which I actually do have a brother. His name's Brian, and I'm going to pretend like he's my twin brother. He's actually 7 years younger than me, but that's my brother Brian, and he's going to be red. And my brother and I are pretty much alike. We're not really twins. He doesn't have as much hair as me. He's kind of got a weight problem, and he's short, whereas I'm this handsome, strapping guy. That's the way I'm sticking with it, in case he gets to watch this. So anyways, we're twins, and this is our 51st birthday. And lo and behold, I get this chance of a lifetime. I get a chance to fly to Alpha Centauri, see the cool empty space between us and it, and then return. And actually, I'm going to draw Alpha Centauri as if it's really small, but it's actually, it's a star, so it's way bigger than our planet. And actually, it's I'm going to say it's essentially 5 light years or 4 light years away. In reality, it's actually more like 4.3 light years, and it's a double star system. So sometimes one of them's closer than the other. But what I'm going to do is I'm going to catch a ride on this kick butt spaceship that happens to be flying by. And in fact, I'm going to go 96.83% of the speed of light. So the spaceship comes flying by like this, and it's traveling at 96.83% of C. Okay. I am going to teleport myself to that. So I'm going to go, and I'll be on top of the inside the spaceship now. Okay. And I'm going to fly in that ship really, really far and get all the way to Alpha Centauri, which, like I said, is about 4 light years away. And the spaceship is going to arrive right here. Of course, it's going to be Lorentz contracted too, so it's going to look a lot squattier than this. But anyways, it's still moving at 0.963. Let me make sure I got my numbers right. Stop bugging me. 9683. Yeah, that works. Stop it. Okay, so 96.83 C. Okay. Now, what's going to happen when I get there is another cool craft. It's even fancier. Is going to be flying by this direction, also at 0.9683 C. So I'm going to teleport myself from there onto here. Okay. And then when I get back here, (0.9683 C), I'm going to transport my nary little butt back to there. Okay.
You just went in a giant circle?
Yes. Yep. I just went in a giant circle. Of course, it could have been a jarring trip, but either way, I went in a giant circle. Okay. So when I come back, I am now, let's do the math. So I basically traveled 96.83% of the speed of light. And one of the speed of lights that you can use is the speed of light C is equal to 1 light year per year. Right? So if I want to know time, remember X equals V times T. So T is equal to X over V. So if I want to go 4 light years, and I want to go at 0.9683 C, then basically that's going to be 4 divided by 0.9683 times 4, basically. So when I divide that 4 by 0.9683, again, I grab the calculator whose battery's dead, not helping me at all. Okay, 4.968. I'm using a HP calculator. That's why I'm saying everything backwards and stupid. So I'm doing 4 divided by 0.9683, and I get 4.13 years. 4.13 years to here. And of course, it's 4.13 years back. So I'm 8.26 years older, or excuse me, my brother's 8.26 years older. So now when I get back, Brian, my brother, is 8.26 years older. So he's 59 years. And of course, 0.26 is about a quarter of a year. So that's 3 months. 59 years and 3 months old. He's kind of vain. That really bother him. He tries to date younger women and stuff like that. So this is really going to be a bad thing for him. Meanwhile, I am, because of time dilation, okay, I get delta T is equal to 8.26 years divided by the square root of 1 minus 0.9683 C over C, quantity squared. So my total time is actually going to be quite a bit different. So I'll do 1, and then I'll do 0.9683. I'm going to square that. That gives me 0.9376049. I'm going to subtract that from 1. That gives me 0.06239511. I take the square root of that. That gives me 0.2497. So you can see it's roughly really close to 1/4. And in fact, now I'm going to divide that by 8.26. Or divide 8.26 by that. Sorry about that. And lo and behold, whoa, that didn't work out. 8.26 years. And now I'm going to divide that by, so I'll do 1.9683 squared minus square root it, divide by. Bopido. Okay, my calculator is really jacking up. But anyways, I'll take this 8.26 and I'm essentially going to divide it by the 4, because I get time dilated because you guys are seeing my clock moving. My clock, my biological clock, is moving at the same speed as me. So I'm actually measuring proper time. And my proper time, of course, is going to be shorter. Oh, that was what I did wrong. I was blindly putting it in the wrong slot. My proper time is going to be elongated to your 8.26. So what I say is delta T is equal to gamma delta T0. So 8.26 is equal to gamma times delta T0. And the delta T0 is how much I age by. So I can see that delta T0 is going to be equal to 8.26 divided by gamma. So this is years. But divided by gamma means times the square root of 1 minus 0.9683 squared. Okay. Now if I can get my calculator to work. So 8.26, I was doing it right, but I was doing it because this HP basically makes me do division, put the numerator first and then enter the denominator and then hit divide. I was doing it upside down and I kept getting something weird. But now I'm doing 8.26 times the square root, and that'll help it a little bit easier, or help make it a little bit easier. So I'll do 1 again, 0.9683. 3, it won't push for some reason. Okay, squared. Subtract 1, subtract that from 1, take the square root of that, and now I'll multiply that by 8.26. And lo and behold, I get 2.06 years. So when I return, I am 53 years, and 0.06 is 6%. Really, that's in a few days. Okay, now this is where Time Life Books made their mistake. Okay, remember I told you Time Life Books and a lot of people made mistakes about this. They think this is the twin paradox. This is not a paradox. This is actual fact. And that's probably the most important thing for you to learn from this particular paradox is this is fact. Okay. The paradox is when my brother, I told you he's a little vain, when my brother tries to claim, no, this did not happen at all. My brother is actually the older one. My brother's now 59 years and 3 months. I'm only 53 years and a few days, because what actually happened was I was just sitting here and lo and behold, the Earth and Alpha Centauri took off going this way in outer space and flew about 4 light years away, and then all of a sudden turned back around and came back and flew about 4 light years this way. And meanwhile, my brother's just sitting still in that dumb spaceship, and returns back when I get back and is all like, oh, I'm younger than you, blah, blah, blah. Okay. Well, at the end of the day, one of these has to be right, because it's obvious, one person's going to look old and the other person's going to look less, not as old. Okay. And in fact, the problem is it's not a paradox. And the reason why it's not a paradox is you can do an experiment to determine whichever happened. Okay. So the experiment I like to use involves fuzzy dice, which I'm going to say my little brother wears fuzzy dice on his ears all the time. Anyways, so. Just because.
I did have a question, Professor.
Yeah. Mm-hmm.
You said that the 8 or so years, isn't that the time that it took for you to travel that? So wouldn't you have to dilate that time?
Yeah, that's basically what well, let me see. You're using dilate, and dilate means to make big. But in fact, what we're doing is we're actually contracting that time, which is the improper time, because according to Brian, the Earth, and Alpha Centauri, I was the one moving, so I was measuring proper time. Brian and Earth and Alpha Centauri said that took me basically my velocity, which is 0.9683, divided, or distance divided by that velocity, gave me about 4 years there and about 4 years back. My time dilation factor was about a factor of 4, so I was about 2 years older. So yeah, you're not dilating my time, you're actually contracting their time to get my time.
Oh, okay, because I was thinking that the 8.26 was T0.
Yeah, it can't be T0 because that is the actual time that Brian and the Earth and all them measure.
Oh, okay.
Does that make sense? It's easy. I mean, you saw me put it in the calculator wrong. So yeah, you're totally right. It's easy to get those mixed up, but you got to always remember which person is seeing that clock you're talking about measuring time, is seeing that not move with respect to them. So if you're talking like a biological clock, like my life or whatever, then clearly I'm measuring proper time. Okay, just like the WHO was measuring proper time as well. All right, so now that we got that, what I'm going to tell you is that the trick to this is, of course, fuzzy dice. So back in the 80s, and it's probably coming back off and on now, people would hang literally fuzzy dice from their rearview mirror. Okay, I don't know why, but they did. So let's imagine me and my brother wearing fuzzy dice earrings, which, like I said, I told you my brother probably does that already. He's a weirdo. So if if in fact I did go to space and then return and come back, then I would be able to detect that by my fuzzy dice moving. And if Brian went, I would be able to tell by his fuzzy dice moving. Well, when I took off, I went from 0 to 96.83% of the speed of light. So clearly my fuzzy dice would have shot back that way. Then when I teleported from here to here, my fuzzy dice would have tried to keep going that way. So they're going to sling really far that way. And then when I teleported from here to here, my fuzzy dice would have tried to continue going that way. So they'd sling that way. I've got 3 instances where my fuzzy dice swung quite well. Whereas the whole time, if Brian literally stood in that particular spot on Earth the whole time, his fuzzy dice wouldn't swing at all. Okay, he could actually detect that. If in fact the Earth and Alpha Centauri took off and went this way, then he would actually have his fuzzy dice swing. So there's a good experiment we could actually do, and in fact, there's no paradox at all. The fact is that 2 people that were twins that were celebrating their 51st birthday the day this thing started. One of them is now 59 and 3 months old. We call him Brian. He has very little hair. He's short and fat. And there's Billy, the handsome older brother, who's now younger and is only 53 years and a few days old. Any questions on that? So that's kind of a crazy paradox, but it was one that was settled, and it was one of the initial arguments about why special relativity couldn't be right. Of course, there is another side to this, and if Brian could get away with saying that he actually went, 4 light years this way and then 4 light years back, if he could actually say that, there would be a paradox. And in fact, that would be the case if the universe was sort of spun back on itself like a sphere. Okay. So for instance, if we were in a universe whose circumference was, let's say, about 8 light years, then a scenario could actually happen. The scenario could be that as I flew this way to Alpha Centauri and Earth might have actually gone this way instead, and Brian's earrings would never move because space is just going around in a continuous line. So that's my argument for this paradox could actually suggest that the universe can't be closed. It can't be a closed loop on itself. Of course, that might not be very good of an argument because it might just be prohibitively large, but yet still closing on itself. In fact, that's an ongoing question in cosmology and physics, even though we think our universe is flat and not closed, but going on forever. There's still some slight chance that it could be a closed universe shaped more like a giant sphere or something like that, but not necessarily inside of anything. That's the weird part. The Big Bang created the universe, which includes the space itself, and that's a kind of hard thing. If it doesn't hurt your brain to think about it, you're not understanding it well enough. All right, so that's one paradox. Now there's another paradox, and this one's a lot easier to grasp, by the way. So what we're going to do is we're going to turn the camera back on, and I'm going to talk about the ladder and the barn paradox. Ladder and the barn. Again, I'm going to put paradox in quotation marks. Okay, so I'm going to build it up because I'm a storyteller. I'm a raconteur, as they say. So there's this young man, he goes away to college, not unlike you guys. Y'all first get to college. I know I did. When I first got to college, I was like, I was learning all this new stuff that I knew my parents probably hadn't heard of. And I'd tell them, I'd be so impressed and blah, blah, blah. Of course, life teaches you a lot of things. Even if your parents weren't fortunate enough to go to college, they know a lot of stuff that we don't know. But you're kind of young and dumb and stuff like that. So this young boy, he gets to go away for his first year at college. He goes to NC State. His father's a farmer. His father went to NC State as well. NC State has a great agriculture school, and he goes to NC State, but he's doing it to get away from the farm. He don't want to be a farmer. He wants to be something giant and awesome and stuff like that, and wants to get away from the farm. But you know, he's also a little cocky, so he likes to go back and always wanting to one up his dad, like a lot of kids want to do. At one point, they want to do it. For a long time, they just see their dad as like this god creature, or their mom is like this god creature, or whatever. But he comes back from college one summer, and he pulls in the driveway of their farm, and he looks out there, and he's like, "Oh, there's that stupid ladder and a stupid barn." And he gets in there. He waits a while. He bides his time. He bites his tongue a little bit. And they're sitting at dinner, and they just finished. And finally, he says, "Dad, I've been gone a whole year. Why ain't you put that dang ladder in the garage or in the shed?" And a barn, I should say. And the father says, "Boy, I don't know what they're teaching you up there at NC State, but when I went there, they taught me that a 20-foot ladder will not fit in a 10-foot barn." And the boy's like, "Well, I went to NC State and I got a course in relativity, and it turns out you can fit a 20-foot ladder in a 10-foot barn." And the father said, "Yeah, okay." Actually, the father's a little smarter than you might think, because he knows what's going to go on. He said, "Well, son, you know, I'm getting old up in my age and stuff like that, and my joints are aching, so I can't do any of the motion. So you're going to have to do this experiment yourself. So why don't we walk outside and you tell me what you're going to do, and then I'll let you do it." The boy says, "Yeah, of course, no problem, Dad." All right, so that's the buildup of the story. So here's the plan. I'm turning on my document cam, and it turns out there's this nice, neat little barn, and the barn looks like this. There's part of the roof. You know, it's got one of those Aberdeen type barn roofs or whatever. It's got planks on the side, so on and so forth. This thing is definitely 10 feet long. And of course, there's also the ladder lying alongside. And the ladder looks like this. And of course, the ladder is in fact 20 feet long. So that's no problem for the boy, though. The boy says, "All right, Dad, here's what I'm going to do. I am going to pick up that ladder, and I am, in fact, going to run at 86.6025% of the speed of light, giving me a gamma factor of exactly 2, so that I can Lorentz contract this here ladder and it'll fit." So what I'm going to do is I'm going to pick up the ladder and start running. So here's the boy with the ladder. And the boy's holding it, and he's running really hard like this. And all of a sudden he realizes the error in his plan, because as he starts to run, he sees the barn, which was a whopping 10 foot long, is now a whopping 5 foot long, but exactly as tall as it was. And he had told his dad, "Hey, Dad, when I get there, what's going to happen is my front of my ladder is going to line up with the back edge of the barn, and the back of my ladder is going to line up with the front edge of the barn, and I'm going to be in the middle, and I want you to slam the door shut. And then that will have the barn fitting in there." So this is the son's perspective, our frame. So the boy sees the problem. He's like, "Oh, crap, I'm moving at 0.866025 C. And this is now 5 foot long instead of 10 foot long. And my ladder's still 20 foot long." Right? But from the dad's frame, the dad sees this. He sees his boy, for starters, he's a lot more vertical because he's been length contracted himself, parallel to the motion. He sees the ladder being exactly 10 foot long now. And he sees the barn being exactly 10 foot long now. And what he sees is, sure enough, when the boy's front edge of the ladder gets in line with the back edge of the barn, and the back edge of the ladder lines up with the front edge of the barn, the boy is in fact inside like this, and he slams the door shut. So the big question is, at the end of the day, did the ladder fit or not? And that seems like a perfect paradox, right? These are both valid scientific conclusions, but they're contradictory. But here's the problem. Anybody see the problem before I state it?
An object doesn't actually physically contract, it just appears to.
That's the normal, that's what most people say in general.
Well, is
they
it because he's still moving?
Nope, it's not that either. It turns out it's actually kind of weird. What we've learned so far is that a time interval that you measure like proper time or whatever is variable. So what you call 2 seconds long, someone else might consider 1 second long. But the weird part is from that equation, time dilation, you get delta t is equal to gamma times delta t 0, meaning if either of those time periods are 0, then the other one's automatically 0. But what we just found is, in fact, that a time interval being 0 is not a guarantee that the time interval will always be 0 from every reference frame. Because here's what's going on. In order for the ladder to absolutely fit, you've got to have a simultaneous series of events. So the front edge of the ladder has to line up with the back edge of the barn at the same time as the back edge of the ladder lines up with the front edge of the barn and the father closes the door. Those three things are all simultaneous. In that frame, they happen simultaneously, and therefore the ladder did fit. But in this frame, what we saw happen first was the front edge of the ladder got to the back edge of the barn. Then we saw the front edge of the ladder blow through the back, and then we saw the boy blow through the back at a Wile E. Coyote type of sort of way, leaving a body-shaped crash mark. And then a split second later, we saw the back edge of the ladder line up with the front edge of the barn. And those three events, or four events now, including Dad closing the door, those are entirely not simultaneous. So both answers are actually right. It's just the definition of fitting in the garage hinged on simultaneity, and it turns out simultaneity is now a relative thing. So the ladder in the barn paradox isn't a paradox because there's no such thing as at the end of the day, did the ladder fit or not? Because that requires simultaneity. So it's a little less it's probably equally as unpleasing as the answer to the other paradox, but it's not a paradox. As you can tell, it hinges on that simultaneity. So our time is almost up. Let me go ahead and give you some equations. It turns out you can derive time dilation and length contraction with the Lorentz transformation equation. So if you imagined x-axis and a y-axis here, and then sometime after t equals 0, you imagine an x prime axis and a y prime axis here. And in fact, at t equals 0, you'd have to have the origins at the same place and the y's and the x's at the same place. In other words, this would have to be right on top of that, perfectly aligned at t equals 0. Now, what's happened is in that time period since, this distance is v times t. And in fact, this distance out to this particular point is x prime on this frame. But in this frame, it would be vt plus x prime. So Galilean relativity would tell us that x is equal to x prime plus vt. And of course, y is just equal to y prime, and z is just equal to z prime, and t is just equal to t prime. That's Galilean relativity. That's how you transform your coordinates from this coordinate to that coordinate. Okay. Now, if you wanted to do the opposite, all you got to do is replace the v with negative v, and that would and flip the prime signs with the non-prime signs. Now, in Lorentz transformations, which is the relativistic correct ones, the same frame can be used, but it turns out the answers are quite different. You still get all x's on this side and x, y, z on this side are primed. So I'm still going to get x prime plus vt, but t and t prime are no longer equal. So everything on this side will have a t prime in it. So it turns out the difference is it's got that stupid gamma factor again. and y turns out to be just y prime, and z turns out to be just z prime, and t, check this out, it also has a gamma and the t prime, but get this, it's even weirder than that. It's got a v, where v is the velocity of this frame, of course, times an x prime over c squared. So that's the actual transformation according to relativity. You can use this, like I said, to derive the time dilation or the length contraction formula. And if you wanted the other version, you just do x prime is equal to gamma x minus vt. X prime, or excuse me, y prime equals y, z prime equals z, and t prime equals gamma t minus vx over c squared. So that's all you got to do to change to the other frame. So that's a neat new set of equations you can use to do your homeworks and stuff like that. And be advised, the homework set has one problem where they give you some parts of the x prime coordinate system and some parts of the x coordinate system and ask you something else. So be on alert, know which coordinate system you're working with. But from that, we can get, like I said, delta t is equal to gamma delta t0, or L is equal to L0 over gamma. But we also get things like P is equal to gamma mv, and F equals ma, or F equals dp dt. The summation of the forces turns out to be d by dt, not of mv, but of gamma mv. So that's Newton's second law now. Kinetic energy is no longer 1/2 mv squared. In fact, it's gamma minus 1 times mc squared. And we've got this neat new value, E, the total energy squared, is equal to P squared C squared plus M squared C to the 4th. And we also got this neat new addition of velocity formula. This one I already showed you, but the velocity of A as seen by C is equal to the velocity of A as seen by something else plus the velocity of something else as seen by C. Notice the outer ones match. Then in here, I just make sure the middle two match. That was the Galilean form, but relativity changes it such that it's 1 plus VAB, VBC over C squared. So that's more or less a brain dump of the rest of the equations we have for relativity. But I will use all those in our next meeting. Class is now over. You guys, of course, are, wait a second, we start at 12:30. So no, we're supposed to go to 1:45, aren't we? I think that's the case. That gives me a lot more time. I'm very excited if that's the case.
Yes, sir. We did go to 1:45.
Yeah, we do go to 1:45. Right on. Woohoo. Okay. So that means I can solve a couple more problems. So as I said, I wanted you to have all these equations. All of this stuff comes from it. Your book does some derivations of stuff. We've done this one and this one in deriving ourselves. I've showed you that the F equals ma becomes F equals dp dt is the general form of Newton's second law of motion. But now I've told you that, in fact, the dp dt has to use the relativistic p. Okay, I've told you this kinetic energy is this. So we've done a lot of stuff. Now, what I first want to do is use this equation and show you how cool that is. So let's do that. So what I'm going to have is I'm going to imagine Earth down here. So this is example 3, I think. Let's imagine Earth is down here, and I have a spaceship traveling at 3/4 the speed of light, and that spaceship is called A. So this is VAE, the velocity of A as seen by Earth. Okay, sorry, I was writing that outside the page. Okay, now I have another spacecraft, B. Now we have to actually all agree on which way is the positive axis and all that good stuff. So this one, in fact, is moving at VBE equals negative 7/8 C. Okay. So what I'd like to know is, what is the velocity of B as seen by A? There's our question. Okay, the velocity of this ship as seen by that ship. For starters, we all have to agree things going to the right are positive, things going to the left are negative. So I expect this answer to come out negative. And in fact, if it wasn't for relativity, we'd expect from Galilean relativity that this is 6/8 that we're going towards it, and this is 7/8 that it's going towards us. So those two should add to give us 13/8, right? So it should be bigger than the speed of light. But watch what relativity does. So here's our solution. I'm going to do it in blue. So VBA, using our general rule that I taught you before and just mentioned to you again, I'm going to say it's VB, leave a blank, plus V, leave a blank, A. Now in relativity, I have to add this down here. Okay. Now I got to find something that matches. Well, I see I have a VBE, so might as well put VBE, and then this one has to be an E. But I don't have a VEA, but remember the rule, VIJ is equal to the negative of VJI. So I can now compute VBA is equal to VBE, which is negative 7/8. I'm going to factor out the C. Plus, now VEA is the negative of VAE. So I got to put a negative on the 3/4. And then I put a C outside. That's just me factoring out the C. Okay. Now this becomes 1 plus negative 7/8 C, negative 3/4 C, all that over C squared. Well, again, I tell you, this is to make a common denominator. This is 6/8 plus 7. That'd be 13/8. So I get negative 13/8 C, which is the Galilean answer. Under here, on the other hand, I get 7 times 3 is 21. And then 8 times 4 is 32. So I get 1 over 21/32. Well, this is 32 over 32. So I'm going to say this is negative 13/8 C divided by, when I add 32 to 21, I get 53. So that'd be 53 over 32. So I can now say that VBA is negative 13/8. Now, dividing by a fraction is the same thing as multiplying by its reciprocal. So I'm going to do 32 over 53. And of course, the 53 is a prime number, just like the 13 is. And I still have the factor of C. But this is 4 times 8, and this is 8 times 1. So those 8s cancel out. And of course, 4 times 13 is 52. And then the 8's gone now, so I just get 52/53 C. So yes, it's surprisingly close to the speed of light, but it is not the speed of light. Isn't that wild?
Yeah, no one really puts a wrench in the monkey.
Yeah. Here's another example. This one I'm going to call example 4 really quickly, and it refers back to this one. What if A fires a photon torpedo toward B? V photon with respect to A is obviously positive C. So what is V photon with respect to B? And B, what is V photon with respect to Earth? Okay. So that is kind of weird, right? Well, let's work it out. So velocity of P with respect to, and by the way, a photon torpedo, photons are the particles that carry light. So they're massless and they actually travel at the speed of light. So VPB is going to equal VPA, because that's the one I happen to know, plus VAE, or excuse me, B. Remember, the outers have to match PB, and then the inners have to match each other. And then 1 over VPA, VAB over C squared. Well, PA, we already know that's C. Now, AB, we actually know BA, and that's negative 52/53. So to get VAB, I got to multiply that by a -1. So I get a positive 52 over 53. Y'all might even be seeing the answer already. This will be, again, 1 plus. Now I get 52 over 53 C times C over C squared. So I think you can see that the C's here cancel out, and I get basically 1 plus 52/53 over 1 plus 52/53, but C in the top. So lo and behold, the velocity of the photon with respect to B is just C. But that's, that's what Einstein said. The speed of light is a constant independent of the motion of the source or the motion of the observer. So now let's try part B. So part B, we want VPE. Well, VPE is VP to something plus V something to E. Well, I could do PA and then AE. That works fine. 1 plus VPA VAE over C squared. The velocity of the photon as seen by A is C. The velocity of A as seen by E is just 3/4 C. And then 1 plus C times 3/4 C over C squared. I think you again see that's 1 plus 3/4 over 1 plus 3/4. Only this one's times C. So again, I get C. Ain't that cool? So your book actually gives you the other forms, because it's not necessary that the frame only have a velocity, say, in the X direction. You could actually have the frame have a velocity, and your book calls it U, and it could have a U, X component of U, a Y component of U, and Z component of U. You might need those for some of your homeworks and stuff, but I'm not going to give you any test questions on that. I'm just going to do straight inline stuff if I do any of these addition of velocity problems. So that might make it a little easier for you. By the way, I did mention that I have an equation sheet on the links and documents now, and I updated the video list on the links and documents. So make sure you check that out. Anybody have any questions on this? All right, so we did do at least addition of velocities. I will do some momentum and kinetic energies next time. Go ahead. I think Austin or somebody was trying to ask something. Anybody? Tristan?
Yeah, back to the ladder paradox.
Uh-huh.
Is this due to the? Is this because the sun's view? Is this because it's due to this observer's view, and then we're not the observer? What about a third party? I could see in between both of them.
Yeah, if someone's moving at, say, instead of 0.866025 C, someone could be moving at, say, 0.43 C, and they would see it completely a waste. They'd see the ladder shrunk to more like 13.5 feet or something like that. And they would see it not a simultaneous event either. In fact, the only frames that would see it as actually fitting would be the father's frame and any frame that caused the boy to appear to be running faster. So like if someone was running towards the boy at some velocity approaching the factor of the speed of light, then yeah, all those frames would see the thing shrunk even smaller and actually see the ability of the ladder to fit in the barn. It might not, it still wouldn't be simultaneous though, because the back edge would hit the front edge of the ladder would hit the back edge of the barn, and the back edge of the ladder would already be in the barn, and the father would have tried to close the door long before that. So that would be kind of odd, but it would at least be small enough in those frames. Any other questions?
I'm just thinking about this ladder thing now. It's kind of messing with my head.
Yeah.
Yeah, me too.
When
Really.
when the ladder stops physically in the barn, right?
Uh-huh.
What happens then?
Oh,
So
yeah,
the ladder's already in the barn, right? But what
yes.
happens once it reaches zero in your
Well,
velocity?
it couldn't do it instantly, but it, in some sense, you could limit it as approaching as small an interval as possible, decelerate from 86% of the speed of light to nothing. And of course, yes, it would go back to its normal size all at once and blow out the walls. I think
Okay.
it's some question as to whether it would blow out the back wall, the front wall, or both.
Both.
Hold on a second. My refrigerator's making a noise.
What about if it was if you could somehow get it to continue moving at whatever that speed of light was,
What if
but
you can get
without
the
actually
barn to
moving?
move too? You have
I'm
the
back.
barn and the ladder
like
moving.
phase shifting almost.
So I hear y'all still
somehow
debating.
you keep the ladder moving without actually moving in distance, but you keep it moving at speed of the speed of light.
could you just
without
have
actually
the-
moving.
Oscillates back and forth at the speed of light.
Yeah.
Well, no,
Yeah.
even then it stops, because you're approaching that limit when you go to turn back.
Yeah, when you
What
get
if
to
you
the
had it,
zero,
like-
it's going to expand to 20 again.
What if you had it rotate? Like, how tall is this barn? Is it like a square? Because you could have it literally going like like a circle track, right?
There you go.
So
Yeah,
you're
you can get it
maintaining the
spinning
same
and
velocity.
try to work
Yeah.
out what frequency is. You'd have to assume how long you're allowed to decelerate from 86.6025 to zero, and that could you'd make half that time you'd make that time be equal to half or quarter of time to rotate, because then it would reach its full length in a quarter of time. Then it would start to shrink again for you to take back off. And then just as it got to the door, it would just reach the speed of 0.866025. And then you can do it again. Yeah.
What if the barn starts moving with the boy, away from the boy?
Oh,
but
it
at a
most
slower
certainly
rate?
will. Especially once he
All right,
hits
well,
it.
why is this boy even going to school if he can run that fast in the first place?
I was thinking the same thing.
He's
He's
the Flash.
totally Usain Bolt, right? Actually, I shouldn't say that anymore. Somebody beat Usain Bolt.
Yeah, literally, you have the Flash.
Oh yeah, there you go. Or what's
Oh
this
my God.
what's this Scuzzy athletes that's on that Netflix series or Hulu series or something? It's like it's got a Captain America looking guy, but he's like dirty and scruffy, and he's a horn dog and crap. I forgot the name of that show on Netflix, but it's those kind of heroes. So yeah, that's sort of the fun stuff of relativity. Y'all would really like Ehrenfest paradox too if you look that up. That's basically like a merry-go-round. And the weird part is, the formula for the circumference of a circle is circumference equals 2 pi r, but a radial line is actually perpendicular to the motion. However, when you spin a disk, the ends of the disk are actually moving, and they could move at approaching the speed of light. So you'd actually expect them to Lorentz contract, but they can't Lorentz contract because their formula is 2 pi r, and r is perpendicular to the velocity. So that's sort of a paradox. And a sad guy who's really an awesome physicist, he solved the problem. In fact, he basically sad. He was born with a special needs child that him and his wife worked really hard to take care of. The wife left him, and then he just got fed up with it one day and killed himself and the son because he knew no one could take care of him. But it was really an awful scenario. But he was a brilliant physicist and a close friend of Einstein's. But he solved that problem, and it's written in exactly one book I found so far, and it's a Frenchman's book on special relativity. But
What's
anyway,
the name of the paradox you said? The
Ehrenfest.
merry-go-round?
EHRENFEST.
Can you write it?
Yeah.
Well, if something's rotating at the speed of light, then wouldn't every point on it be contracted almost like simultaneously,
I want to know the
or
motive
be close
behind
enough
that.
to be negligible?
Yeah. So
Where
when you get closer to the
every
middle, the
would be-
speed gets smaller, but everything would be contracting to some extent. But it's like 50th decimal place when you're a centimeter away from the middle, where it can go all the way up to the speed of light at the end of the radius. So that could be an infinite amount of contraction. So it's Ehrenfest or Ehrenfest. I'm not sure how to pronounce it, but That's an interesting one. It turns out the geometry on that is so jacked up. It can be treated with general relativity, but they can also treat it with special relativity, and that's what Ehrenfest did. And he found out that the geometry is such that a triangle is this on that disk. A square is this on that disk. Not only that, you know, one of the neat things that you learned as a kid was, or that you thought you learned as a kid, is if you can't see you, then you can't see them. So they just like cover their eyes, right? And then later we learned, oh crap, they can still see me, right? So that gave us an idea that light has reciprocity, that like no matter how well you hide, if you can see the person can see you. It might be really hard. You might have to use like a small mirror, but they can still see you. They might just see your eyeball floating in space or something, but they'll see you. Well, in this world, on this spinning disk, there is no light reciprocity. Sometimes things can see you that you can't see. So that's some of the weird anomalies with the Ehrenfest paradox. Anybody else have any questions? Relativity is fun. We're going to solve a couple more problems next time, and by all means, definitely check it out. I think there's one homework set available to do on for you guys. It'd be Monday, so y'all get another.
I think the conceptual was due yesterday.
Yeah, the conceptual was due yesterday, but the problems were actually due next time. In fact, I think just because y'all got behind, I think I'm going to push that conceptual back to Saturday night.
Which conceptual?
For 36.
Exactly.
Yeah,
Wait,
for
what?
36. Now
All
there's
right.
2 sets of problems for chapter 36, but I staggered those by one being due on Monday and the other one being due on Wednesday. All right. Well,
Awesome.
I got to
Thank
go
you.
to another class. I guess I best let you guys
All
go.
right. Thank you.
I appreciate your time.
No problem. Enjoyed having you guys. Thanks for coming.
Have a good weekend, Professor.
You too. Anybody else? Noah or Gerald, you have any questions? Got a couple minutes left, just in case. All right. Well, have a good day.